So we just finished talking about acceleration and speed and velocity, and now we're going to talk about forces. So we have a long history of knowing something about forces. Aristotle, in the 4th century BC, was kind of the first person to really record some observations and some statements. And so two of the things that he has stated are that heavier objects will fall faster than lighter objects, and objects moving horizontally require continuously applied force. These are two things that we now know are not true. That because Aristotle relied on thinking alone, he made the observation, he made the hypothesis, but he didn't design the experiment and carry it out. He was missing that last half of the scientific method. But that both of his predictions are wrong. So we're not going to call them laws or theories or anything like that because they're just predictions. He ended up in the early stages of the scientific method. So Galileo and Newton come along, and it's nearly 2,000 years later before we really start to understand how and why Aristotle was wrong. So based on the scientific method and some measurements and experimentation, they both come to the conclusion that all objects, regardless of their weight, will fall at the same rate. And that's because we now know that there's a force that's acting on all objects called gravity. And that's going to determine the rate at which something falls, not its mass. The second thing is that no force is required for uniform horizontal motion, meaning if it's going in the same speed, in the same direction, you can apply the force one time and the object won't need any extra pushes or pulls to continue motion. Now, we know that objects come to a stop, right? If you kick a ball, if you do something like that, or if you stop accelerating your car, it's going to stop forward motion. And we know that that's because there's this opposing force called friction force. And that's what keeps us from sliding and slipping and falling all over the world and allows us to stand on the sidewalk and allows us to stand on the grass. If we didn't have a friction force, everything would be slippery like ice. You know that if you push an object on ice, it's going to go for a long period of time because it's in the absence of friction force, which opposes that forward motion. So because Galileo and Newton based their reasoning on measurements more than just thinking alone, they're given a lot more credit in the realm of modern physics and what we really know to be true. But Aristotle was one of the first to really start thinking about how and why things around us do what they do. So what is a force? Well, a force, as Chris and Julia are showing us here in this image, are any push or pull that's capable of changing an object's state of motion. So it must result in a change of motion. The overall effect is determined by the vectors, so think arrows, sum of all of the forces, which we're going to call the net force on the object. So for example, in this image, you have the upward arrow, which is the normal force. This is what keeps you upright, allows you to stand up. There is a force pushing back up on you from the earth, which helps you stay upright. There is gravity pushing down on you, which keeps you on earth, keeps you from floating away. There is the applied force that will cause a change in forward motion. If someone was to push you, you're going to go forward. And then the other force is the friction force. It's what's opposing us and causing motion to stop over a period of time. When we take all of these arrows and add them up together, we're going to call that the net force. Okay, so if all of those vectors cancel out, then the net force is considered to be zero and there won't be any motion. The other thing is that if velocity is constant, so going at the same speed, the same direction, we're going to say that the net force is also zero. So the net force will be zero when there's no motion or constant velocity. Any other situation, the net force is not zero. It's always going to be something other than zero. Now we have four fundamental forces, meaning they are basic, they cannot be broken down or explained in any other way. The four are gravitational, which acts between all objects, you and the earth and the moon and the sun, the earth and the sun, holds our world together. electromagnetic, which is acting between electrically charged parts of an atom, which we haven't talked about yet, but these are going to be our protons and electrons, which hold our atoms together. We're going to have weak nuclear forces that are involved in certain nuclear reactions, which we'll talk a little bit about in some other chapters. And then we have a strong nuclear force, which are involved in holding the nucleus of atoms together. And this force is actually stronger than electromagnetic and gravitational force. And then obviously it's stronger than the weaker force. So this is the strongest force. So you need to know what the four fundamental forces are. So let's talk about some specific types of motion. So we're going to start with horizontal motion. So the natural motion question is a continuous force needed to keep an object moving, right? That's what Aristotle said, but then Galileo and Newton came along and said, no, not really. So in the absence of unbalanced opposing forces, aka friction force, no, natural motion should continue until all of time in the absence of an unbalanced opposing force. So if we're looking at this right here, the applied force is to the left. So it's supposed to go to the left direction. However, the air is pushing back on the ball. If I can pick a different color. The other one is the floor. So the floor is causing the motion of the ball to stop, as well as the air pushing back on it. So you know that if you're running on a really windy day and you're running into the wind, the force pushing back on you makes you exert harder to continue to go forward. But with that, the ball doesn't have legs to keep running. So when the air is pushing back on the ball and the floor is pushing back on the ball is eventually going to stop because it doesn't have any way to counteract that. So eventually the ball is going to stop moving. Now, if we have an applied force, something pushing on the ball that's going to balance out the force of the air and the force of the floor, well, then you're going to have still a movement to the left, right? And the net force is going to be 0 because it's moving at a constant velocity to the left direction. So in this case, this would be still an example of motion, but because it's moving at a constant velocity, the net force is 0. Now, inertia is a really important part of physics. Inertia is going, and we're going to see this word again when we get to chemistry, but is the measure of an object's tendency to resist changes in its motion, including rest. So, inertia is one of the reasons why really large planes have to have a really long runway, whereas little tiny planes have to have they can have a short runway. They don't have to have as much space to gain that momentum that they need, the speed, in order to take off. Same thing with landing. When a big plane is coming to land, it can't find a teeny tiny airstrip and think it's going to be able to stop. It's going to need a long runway to slow that motion down. And that's because a larger plane has a lot of inertia and a little plane has a little inertia. So one of the ways to think about it is heavier objects have a higher inertia. Now, falling objects. Falling objects are going to be our next topic we'll talk about. Now, falling objects are falling one way, to the ground. We call this free falling if the objects are falling under the influence of gravity without air resistance. And this is going to be a very few instances. So one of the examples are the people who do the cliff jumping and they don't use a parachute, but they go in like the little squirrel suits. And when they first jump off the cliff, they're going to tuck their hands in really close to their body. They're going to tighten their body up really to almost be like a pencil. And when they're doing that, they're trying to minimize the air resistance on their body so that they can reach really fast speeds. So they're free falling and trying to minimize the amount of air resistance. The opposite is whenever they open up their arms and their legs and they're wearing like these squirrel suits that have wings, and all of a sudden they're increasing their surface area of their body, which then increases the amount of air resistance they're feeling and then slows them down a lot faster. So this is the same thing that flying squirrels do, and so they're just one example of free falling and then how we can increase the air resistance. So most all objects are going to fall with air resistance as a factor, okay? But whenever we don't have air resistance, the velocity is going to increase at a constant rate. So if we see here the ball being dropped from the building, each second that goes by, the ball is going to travel larger distances. So in the first second, it goes 4.9 meters. In the second, it's going to have gone 19.6 meters. So we can see that it's traveling longer distances with each second, but that's not because of distance, it's because it's increasing in velocity. Okay, so it's actually increasing in its speed because the direction is not changing. The direction is still going down, but the speed of the object is increasing until it hits the ground. Now, the acceleration that the object is feeling is due to what we call gravity, lowercase g, which is the same for all objects. And this is why Aristotle was wrong when he said that objects with different masses will fall at different rates. And that's because it's not the mass that determines the object's rate of falling, it's gravity, when you neglect air resistance. So if I took a tennis ball and a piece of paper and I dropped a flat piece of paper and a tennis ball, I'm going to see that the tennis ball is going to fall faster than the paper, but that's because the paper has a lot of air resistance. If I take that same piece of paper and I crumple it up into a ball that looks like the tennis ball and I drop them, they have similar air resistance effects, and they're actually going to hit the ground at the same time, even though the tennis ball is going to weigh more than the paper ball I just made. If you don't believe me, go try it. The only difference between the flat paper and the crumpled paper is the amount of air resistance they're feeling. And if everything could lack air resistance, all objects, no matter what, would fall at the exact same rate, and they'd hit the ground at the exact same time. Now, the value of gravity, little g, is important. It's 9.8 meters per second squared, or 32 feet per second squared. Now, we typically don't see this one. And then sometimes the value of gravity gets rounded up to 10 meters per second squared. But 9.8, 10, pretty close to each other. So now we're going to talk about our third type of motion, which is compound motion. And we have three types of compound motion. There's vertical, horizontal, and then a combination of 1 and 2, which is vertical and horizontal. So when we talk about compound motion, sometimes we're going to talk about a specific type, which is called projectile motion. And this is when you have an object that's thrown into the air, thrown up, thrown over, but it's going to be thrown. There's two basic observations about compound motion that are important. One is that gravity acts at all times. Gravity is not like a light switch. You can't turn it off and on in most instances. It's always going to be on. So it's what is driving most of the downward pull that our objects are going to feel when they're up in the air. Now, acceleration, g, is going to be independent of the object's motion, meaning it doesn't matter if it's going vertical, horizontal, or a combo of the two. Acceleration is always going to be due to gravity, and gravity is always on. So it's always going to be what's bringing our objects down. So in projectile motion, we can think about it two ways. There's the free falling, a child up on the branch is dropping a ball, or a person hits a golf ball, it goes up in the air and then hits further down the green. So with a vertical projectile, we are going to see that as the object goes up in the air, it's going to travel, and as it gets closer to the peak of its traveling up here, it's going to start slowing down. So we see that the arrows get shorter, right? This is a longer arrow, a little bit shorter, indicating that the velocity is slowing down. At the top of the peak, the velocity is going to be 0. So it's going to cease motion for just a little bit. And then it's going to start traveling back down. And the velocity is going to be a smaller value, then a larger value, then a much larger value until it hits the ground. So it's going to slow on the way up, and it's going to accelerate on the way down. And the acceleration is going to be due to gravity. Now, the other thing is the force of gravity acts downward throughout. So when the ball is traveling up and we see these upward arrows, there's also going to be a downward pull on the ball due to gravity. So the ball is slowing down because of gravity, but it's also speeding up because of gravity. The only thing changing is the direction. When the object is traveling against gravity, going up, it's going to be slowing down. When it's traveling with gravity, it's going to be speeding up. Now, a horizontal projectile is going to have an extra component, which is a horizontal velocity. So instead of up and down, it's going to be left to right. Remember, horizontal is around the horizon, vertical is up and down. And the horizontal velocity of this type of motion is going to remain the same if we're neglecting air resistance. Okay, so pretending there's no air pushing us backwards. And then the type of path it's going to take is curved. So it's not going to be up, down, it's going to be curved of some sort. So fired horizontally versus dropped. Is there a difference between firing an arrow and dropping an arrow? Well, we could say yes, that in some ways the shape it's taking, its path is different. However, there's something really unique that's happening. The vertical motions occur in parallel. So we see here that these downward arrows, this is gravity. Remember, gravity pulling us down. We see gravity here pulling us down. But with the horizontal motion, there is now this arrow that points to the left, from left to right, which is what's allowing it to travel over a distance instead of just falling straight down to the ground. Now, that additional component isn't going to change the amount of time it takes for the object to hit the ground. It's still going to hit the ground at the exact same time that the arrow that's dropped does. The only thing is that the horizontal velocity component is constant. After the arrow is fired, it's not going to speed up and it's not going to slow down. It's just going to stay constant. The thing that's changing is gravity is increasing its ability to pull the object down. So they're still going to hit the ground at the exact same time. If you don't believe me, go try it. So here's another example, passing a football. So if we look at passing a football, we have, he's going to throw the ball up. Eventually, so at first it's going to go up. It's going to start slowing down. Velocity is going to hit 0 up at this top part. And then we're going to see that this right hand motion is going to continue. But we have this additional component of the downward. So remember, when it's going with gravity, it's going to speed up. When it's going against gravity, it's going to slow down. And then we have the horizontal component where it stays the same. So once the ball is thrown, it's not going to speed up left to right. The only part that's changing is the slowing down and the speeding up due to gravity. But regardless, it's going to have a downward acceleration throughout because the ball will not get thrown up in the air and just continue, right? There'd be no person, there'd be no receiver over here if the guy threw the ball and it never came back down. So we call this path that it's taking a parabola. Okay, so we see that vertical velocity decreases and then increases, just like throwing the ball up in the air, the golf ball up in the air. But the horizontal motion is uniform, just like firing the bow and arrow. The combination of those two motions creates what's called the parabola, which is just like half of a circle. All right, so we're going to take a break and then we'll talk about 3 laws of motion in our next video.